I'm really very happy to be here. And I'm very happy that I managed to arrive. Had some problems that are no more with me. At least most of them are no more with me. So, and I told Lars actually many times, I'm quite surprised to see how big and actually versatile the department is, and in terms of communication and information theory orientation. Knowing many places in Europe, I just see no comparison. So, again, very happy to be here, and thank you for the kind invitation. So today, I would like to speak, again, taking the information theoretic perspective on something which has practical implications. And to be specific, it boils down, summarizes down by the word robust, meaning maybe not optimal from this or another aspect, but something which probably is here to stay, is kind of maybe appealing also not only from the theoretical point of view. And whatever I'll focus in our talk today is decentralized processing or communication via decentralized processing, and mention different models and different results. And the whole talk is based on some studies done with different studies done with my co-authors listed here: Elsa Erkip, Andrea Goldsmith, Denis Gundus, Vince Poor, Amichai Sanderovich, Osvaldo Simeone, and Ofer Somek, from many places. So cooperative communication is truly no new phase now, a very timely concept, and it promises capacity, coverage, reliability, many things, but still seems to be more of a theoretical tool. Important, but still theoretical. Why? Because it's actually not that easy to imagine practical system that cooperates many distributed antennas like there were in the very same location, for example. This kind of ideas find applications, at least either are thought about in future standards, in cellular networks, companies like Huawei, who I understand has an operation also here, and ad hoc networks. And in many scenarios, the cooperation is actually out of band, meaning it doesn't take the resources or part of the resources where the mainly communication goes. Like, for example, my cellular, not with me here, but right there, can connect via Bluetooth to something else to help to improve the direct communication. So very simple examples, and I'll try through the talk, actually not to cover too much details, but more give the intuition and the impression. So we see here a heterogeneous network with terminals that can work on different standards, and some actually are multi-standard terminals. So say S1 wants to communicate to D1 and S2 to D2, and we want some kind of a helper, a cooperation. R stands for a relay, which actually works on another standards. So this accounts for out-of-band cooperation, meaning the cooperation, if it actually occurs, doesn't take resources from the direct link. Another example, simple cellular systems called now also MIMO networks, sometimes massive MIMO networks, where a central processing unit does all the decoding and encoding, and all cells, which are actually here, the cells, they do not operate by themselves with, in fact, the antennas and the equipment, but convey, transfer, transmit the information to a remote processing so it can decode based on not only on this cell site or the other, but jointly. We'll see the advantages of that if existent. Another example, also timely, femtocells. Femtocells mean local cells at the home, at the building, which kind of assist the network, meaning that it's not that home users are not received by the macro base station. They are, because we don't need a femtocell in order to operate. But if there is some, maybe that can enhance performance. And those femtocells are connected to the main central processing unit probably via internet, via optical cable or whatever. So the issues we will try to address is cooperation, but cooperation in a heterogeneous network and distributed scenarios, trying somehow to model in a little more accurate the quote-unquote, the real-world scenario, where the focus is on the robustness, as I said, and what does robustness mean here? Imperfect information regarding the codebooks. Not every node, everything knows everything, all protocols or codebooks, everything that there is, like the basic information theoretic assumptions of multi-terminal, multi-user networks. That we will depart. That's one thing. Another thing, imperfect information regarding or about the channel state. And that we'll see what are the channel states for us. Won't be the regular thing like the fading coefficients, so on and so forth. And whatever we'll try to see is kind of an information theoretic framework that captures that all. We'll start imperfect codebook information and discuss two issues: ad hoc networks, relay anti-interference channel, and cellular systems. And when we will discuss a topic, the central reference will appear downstairs, and the slides are here, stored, so whoever is interested is most welcome to look at the details. So what are we talking about here? The first issue, the first topic. As we said, standard assumption in information theory assume that encoding, decoding functions, all operation, protocols, everything is known everywhere. All nodes are potentially aware of all possible strategies and operation. That we wish to depart from. Here is a simple example of a relay channel. Encoder, decoder, and the relay. The usual assumption is that the relay knows everything about the way the encoder tries to convey information to the decoder and tries to help the best it can. Kind of embarrassingly enough, even for the relay channel, we still do not have conclusive capacity results in general. Of course, many cases are so, but not in general. Another model, the interference, the classical interference channel. Here it is. Encoder 1 to send information to decoder 1, encoder 2, without any cooperation, to decoder 2. And both decoder 1 and decoder 2 are aware of everything. All the code books, also from that user, they are not interested in decoding or in communicating with. And still, also here, embarrassingly again, we don't know the general capacity region, but for many cases. In many cases, many regions, but not in general. For such simple a scheme, really, two-user interference channel. Out-of-band cooperation that we see in a relay is when the relay is connected to the final destination, we are out of band, say, through the internet with a finite capacity of C. Very simple model, truly simple model. It's called primitive relay channel still, even here. Under general assumption, the capacity of even of that trivial model is not fully known. And the other picture is the interference channel with the relay, again, primitive relay, where without the relay, it is not known the capacity region. With the relay, of course not. So what are we to talk first about? Is exactly this oblivious regime, meaning that the relay has no information about the encoder codebook. And in the interference channel, the decoders have no information about the other user's codebook. Neither the relay has information about any of the codebooks. How do we model that first? How do we model this information theoretically? This obliviousness to get rigorous result. And what is the ultimate performance limits? The model is actually quite simple. Usually, we have a codebook. What's a codebook? Some table, dictionary, that per each message you have a code word of so-and-so length, a length n, when the length goes to infinity. In order to model the obliviousness in the right information theoretic way, we actually have randomized coding, meaning not random coding the classical way we approach information theory to start with, at least coding theorems, but also the codebook is randomized and determined by this parameter f. W is the message. And what is f here? It runs through all the possibilities. How much are there if the cardinality of each symbol is x, cardinality of x? Each codebook contains to do the nr words, if the rate is r, length n, so n to the two nr variables. That is the power of the cardinality that reflects everything. And f is a random variable, which is not given to the oblivious node. This, once you take this into account, but given, of course, to the legitimate users, otherwise no way to decode. Once you take this into account, things become very simple. Very simple in what way? Actually, the symbols become actually IID. So the structure is lost for that oblivious node. As for the loss of structure, maybe at the end I'll add something, some comment, time permitting. So that's important. Once you take this, immediately the problem, look at this primitive relay, solved quite simply. What is the capacity? Here it is. The maximum mutual information between x, y tilde, or what given q is a time-sharing parameter that obliviousness actually affords. Where y tilde is a version of y3 that can be communicated to the destination via the finite capacity link of capacity C. So C is larger than y3, y tilde, source coding, given y and q. What is that? This is the Wiener-Ziv rate. Remember, y side information is correlated with y3. So this is the Wiener-Ziv rate which assures that Y3 hat can be decoded here, and then Y and Y3 are used to decode X. This is the capacity. And this is the probability law breaks like that. And the central point is, again, binary compression of an inequality. Quite simple. On the brink of being trivial. For the Gaussian channel, if we put here the Gaussian channel, meaning this is the main link, this is the relay link of capacity C, closed form result. When C goes to infinity, this is 0, you get full receiver diversity, like you had both antennas. 1 plus P plus alpha P. Like both antennas were at the same side. Because, yes, C infinity, the analog signal gets transferred to the destination with no additional noise. How about this more complicated relay-assisted, primitive relay-assisted interference channel? Same story. Same story. While the interference channel cannot be solved under this obliviousness, under the oblivious assumption, solved exactly. Again, the very same intuition. You transmit side information here and here a la Wiener-Sieve through the finite capacity links, and that's it. Quite simple. So oblivious is not only a nice thing to have, and it is, because kind of you're not system adapted, but also gives you a way to get very simple theoretical results. Let's look now, let's move away from maybe that very simple code problem model and focus on a cellular system. Again, simple cellular systems, where again, maybe this is a tutorial on cellular published last year, which has much more than the information we have here. Okay, cellular system. We already agreed, no way to process all cell size antennas together exactly. But those cell sites can be connected to the central processor, again, via finite capacity links of, say, capacity C. No matter how, microwave, optical cables, internet, whatever you wish. And here are the cellular antennas, and we have intercell interference. And this is the simple, what is known, soft handoff Wiener model. Why soft handoff? Each cell gets interfered just from the user. Say we have one user per cell. Not too difficult to show that this does not impair actually optimality, considering the case of no fading. Just that user has the total power of all users. And each cell receives its own user, plus the one that is associated with another cell to the left here. This is the Wiener model, soft handoff. Why? On the soft handoff region, more or less you get both users from your own cell and the other cell. Just, of course, a naive, simple model, not beyond that. OK, here is the received signal at the cell site M, the user of M, plus alpha, which is the attenuation factor of the cell to the lab, the user at the cell to the left, plus noise. And the base stations are oblivious. I have no idea about the standards, about the coding used, nothing. What can we do here? The central processor, of course, knows everything. First, an upper bound. The minimum between C and this expression is an upper bound. Why? This is the cut-set bound. If we take the cut here, capacity per cell cannot be larger than C. That's the only way you transfer information. If we take the cut here, what is that? Taking the cut here, it's like all cells, all antennas cooperated together. All antennas cooperated together, it's the classical Wiener result. How do we How come we can't calculate it so easily? How come? Look at the model. This is, in fact, intersymbol interference channel. But the intersymbol interference doesn't take place in time, but in space. But who cares? So the capacity is actually the Shannon 9049, not 8, result. And here calculated in closed form. So this is an upper bound. How do we find what is an achievable rate? Here is the idea. And again, a closed form expression. The achievable rate does the following. Look, oblivious cells. Here it's like we have source coding with correlated sources. Why? The signals here are correlated. The same user is received here and here. So this is the CEO problem. But our measure is not average distortion. It's the rate. Once we know how to operate, and here actually the idea is to do quantization, again oblivious, and decode jointly, not separate quantization level, and that much later got the terminology noisy network coding. Same business, has appeared much before, and in our work, not the first time either. So noisy network coding is no new phase. Doing that, again, closed form result. This closed form result, let's see, for C goes to infinity, again, you get the upper bound, the Wiener result, full cooperation. For P, signal to noise ratio goes to infinity, you get C, the other cuts at upper bound, of course. You get C because that's the maximum you can do. The cooperation matters less now. From that single expression, you can check, which is quite nice. What's even nicer is the multiplexing gain. In Wiener, the multiplexing gain per cell is 1, so like uninterfered because of the joint processing. So it's logarithm of SNR. That's exactly that C should be. So you don't lose here from this oblivious result. And actually more, if C behaves like R log P, then you get multiplexing gain of R. And there's no other way to beat it, oblivious or not. So it's not that bad. We can also characterize quite well the low SNR regime. The low SNR regime, and here is the basic affine behavior by Verdoux, meaning minimum EB over N0 and the slope. Here are the minimum EB over N0 and how you pay for that in terms of C, and the slope also. So let's look at the figure. What do we have here? This model and the SNR equals 10 dB as a function of alpha, the interference factor, where if we take the work of Dr. Roberto Padovani, the former CTO of Qualcomm, amazingly, that data amazed me really quite dramatically, I would say, because the model is naive. You see what kind of. He assured me, good friend of mine, that, look, we have experiments. It's not that bad. Don't ask me. I have no explanation to that. And actually, alpha is something around this region. So here we have the full cooperation. Wiener result. C equals infinity, the blue curve. Look, if C equals 8, this curve, not that far away. And look, if you are in this region and transmit 3.4 bits per cell, what the backhaul should be just twice, about twice. And the loss is minimal. Is minimal with what? With an oblivious processing. Nobody knows anything. A dumb cell site. Not that bad, of course. If C is smaller, you pay. And sometimes you pay big. Do we have better techniques? If we are willing to abandon obliviousness, yes. Structured coding. Lattice-based structured coding, another work that joined with Bobak Natsara, and Michal Sandarovich and myself, and another more advanced idea of these days is integer forcing processing. I won't dwell on that. I won't detail too much. But obliviousness is very important, and you see that you don't pay that much for it. How about the downlink? Uplink was fun, okay, quite expected. How about the downlink? Same business. We want to transmit on the downlink. The central processor has all the messages, knows everything, but unfortunately connected just with backhauls of capacity C. Had the capacity been infinite, no problem. What would we have here? A MIMO broadcast channel. Multi-antennas, all cell sites cooperate. MIMO broadcast, because we have a number of users, that the number of antennas here. MIMO broadcast channel is solved. We know exactly what to do. That's, by the way, the 2007 IT award paper, the MIMO broadcast channel. So we know what to do. But here, we cannot. C is finite. So what do we do after all? The central processor could, in principle, calculate all the vectors to be transmitted from all antennas. So what's the problem? It cannot convey them because of the finite capacity limit. So what does it do? It conveys a quantized version of them. So additional noise. Additional noise, better take it in account in advance, because MIMO broadcast has to do with dirty paper coding, which is sensitive to the SNR. Take that into account, put that all together, a closed form result. A closed form result where this is the degraded SNR, which depends on C. C equals to infinity, this infinity, this 0, no degradation in SNR, well done. Closed form result, as simple as that. Studying this result, C goes to infinity, we go to the upper bound or the downlink, MIMO broadcast, which is exactly as the uplink. Why? The duality principle. MIMO broadcast and multiple access duality. Not new thing. For P goes into infinity, we should have gone to C, but here, because we are not that smart, we go just to C minus 1 plus something, so we lose at most 1 bit. Again, low SNR behavior, minimum EBO over N0 on the slope, and the penalty you pay with C. To see how it goes, here the reference curve is the intercell time sharing, which means more or less, look, transmit different times to even and odd cells, then there is no interference. It's a simple model. And of course, it's alpha independent because there is no interference. And, but look here. This what's more interesting is this yellow curve we just disturbed meets the upper bound, the Wiener full cooperation for what? For C equals what you see here, about 8 point something, where the rate is 3.8, again, twice. You need twice the backhaul, and that's it. And the obliviousness, first, twice the backhaul doesn't cost you much. Next, also obliviousness doesn't cost you much, as compared to the ideal scheme that it cannot be the full cooperation. So once we realize that, let's move another step. Chance state information. And here we will examine femtocells in more details. Again, the full paper appears here. Femtocells, we had this picture before. And what is chance state information? Amazingly and unexpectedly, is this internet, which is so reliable. So it is not. And here is data from Telefonica. This internet is not always reliable, must be enough to transfer whatever you wish. And that's a problem. It doesn't say that it works at rate 0. It doesn't work. But it works with quite a spectrum of rates. Not good. So it's like fading on the internet in terms of the capacity of the backhaul. So here is our simple model. Home users that are received by the femtocell, home base station, and by the central base station, because they work also when we have no femtocells. Outdoor users, only only the central base station. We speak here about the closed access femtocell. Only my own users I service, the others don't care. Okay, so let's consider this system where this red line, the backhaul, will be the random variable that takes so-and-so values. So the attenuation here is 1, here is alpha, and here is beta, standing for the fact that the femtocell base station is much closer than the base station itself. Here is just the received signals, just depicts what we have on the picture. And the capacity of that backhaul link could take several values, CM. The home base station and the central base station, they know, they measure, they see what's the CM, the actual CM. Not known to the end users. The center, yes. So what can we do? Home users maybe know a priori what value CM can take in such another resolution, but not what is the actual link that connects right now, because of all neighbors use the internet or God knows why. Outdoor users, they don't care about anything. They want to transmit their rate independent of what home users does or not. So what we try to do here is the state. The rate, the capacity, quite uncommon, usually uses fading, SNR, whatever, the capacity of the backhaul link. And if we take the classical standard approach, Shannon approach, that we must transmit information, whatever it is, and the state is here to stay. It's not that it changes by the bit rate of the communications, not an ergodic setting. So Shannon dictates worst case design. Worst case design might be not that clever to do here. What if the capacity link is low, but it happens quite rarely? So is it a good approach? Probably not. So what do we do? So Shannon, the classical capacity results is fixed-to-fixed encoding. Whatever we do is variable to fixed channel coding, not source coding. Variable to fixed channel coding, a notion that has been introduced and studied in this work by Verdu and myself. Channel coding, no, not with this example in general. We just use it here. That says that the home users will actually use the broadcast approach. No broadcast channel here. Yet they use the broadcast approach. It's like there are different scenarios with different cells, with different capacity, and for the higher capacity, the higher rate you convey without knowing what is this capacity. It's like a broadcast channel, as we will see, and that's the idea. That is already used in other things like MPEG, JPEG. In coding theory, this can be referred to as unequal error protection code, meaning if the SNR is lower, of course, here it's not SNR, you just decode the made part. It's higher, you decode another thing, errorless. Let's look, why is the broadcast approach? Look, the broadcast channel, Gaussian broadcast channel. This noise N1 is larger than N2, the variance. So on N1, I get just one layer. On N2, the better. Of course, I get this layer, but can decode the other one. Superposition coding that achieves capacity on the scalar broadcast channel. That's exactly what we do, and that is called the broadcast approach, and it has been studied, as we say, indeed for the fading channel by Steiner and myself. Actually, the first work is in 97, not here. So that's what we do here, exactly this. Multi-layer, M layers, the number of cardinality of the backhaul link can take. And the idea is the better you have, the better the internet connection is, the more information that the home users convey without them knowing what is the link. So working things out, and as I promised, I'm not going to go through the details, but things could be worked out. For the Gaussian channel, it looks much, much more compact. Outer bounds can also, we don't have the capacity, still lower and achievable on outer bounds. Outer bounds, the idea is to follow the converse for the Gaussian broadcast channel via entropy power inequality. So let's take an example where the capacity of this internet link is either 0, no internet link at all, still you want the home users to transmit something, or C. And the average rate then is this rate that can be transmitted even without the internet, plus whatever can be transmitted if the internet is there. And putting up numbers according to this Telefonica thing with the home users, which are 10 times using the 1/d to the squared attenuation, free space attenuation. Building everything together, what do we have? First, the worst case, the Shannon design, here it is. Doesn't at all depend on the failure probability of the internet. It plans for the worst case, there's no internet. So it doesn't depend at all. Once you optimize over the parameters, you get this. You get this curve, while the upper bound is still not on that. But again, once you get this curve, meaning that, of course, the optimal strategy is actually the maximum of the three. This is an upper bound not achievable at any. So, well, let's move one step further, and that will be the last step. And here we try to examine cellular networks or network MIMO links, meaning what? Again, central processors. Before we already discussed this, but we had backhauls with capacity C connecting to that. We didn't take into account the reliability of the backhauls as we do now. Those backhauls can be available, can be unavailable, can vary in their capacity. What do we do? Let's first examine a very simple model. Transmitter, central processors, relays, only through the relays, to cell sites if you wish, that the central processors gets this information. which are connected by backhauls. Okay. For the model, from the encoder to all the relays, we have a broadcast channel. From the relays to the final decoder, we have clear links, but they are unreliable. And let's take the following models. Some of the links are just not there. And the user has no idea who is there or not. So out of the M total links, only M could be operative. And M is a random variable. We don't know what exactly it is. The users do not know. The links or the decoder might know. The user doesn't know. And that's a non-ergodic setting, because if the link is not there, it's not there for the whole transmission. It's not only it's here, not here. So it's a non-ergodic scenario. Again, obliviousness, we said. So the processing here cannot take into account the structure of the signals received. Those are code words and not some IID elements. So again, we back off to CEO-based source coding, distributed source coding. And here we will take two approaches. A single description approach, source coding problem, distributed, by Ishvar et al., or a multiple description, more advanced, Chen-Berger result. Fine. Let's take a simple model. So all links here, the broadcast channel, oral equivalent Gaussian channel, same noise. Independent, but the same noise. Totally equivalent. The input is power constrained, so the broadcast part, statistically equivalent observations. The second part, those finite capacity links, we know the probability that there will be M links operative. And say M can go from M0 to M total. M0 doesn't have to be 0. We can assure that out of 1,000, we have at least 127 links. Doesn't have to be 0. We know this probability space, which is measured based on experience. This Telefonica have actually introduced and exhibited enough data about that. And we are interested on the expected rate. How do we operate? Again, this broadcast approach. Broadcast approach, variable to fixed channel coding. Channel coding, variable to fix. That's depends on the state of the receiver, the rate that you decode. So we have the number of layers goes from M0 to MT. And the idea is we decode all the layers from the worst one, M0, through some point here, M, provided that M links are operative. If M is lower, we decode less layers, starting from that up to the number of links that we have that are operative, and this is the actual rate. The sum from M0 to M of the rates. And remember, obliviousness is with us. Upper bound is quite simple. There are some of them. Some of them can assume either ergodicity on those links where we don't have originally. And things could be worked out, of course, with auxiliary parameters. For the Gaussian thing, Gaussian model, much more simple and compact. Result, as you see, whatever we have to optimize is over the parameters B, M0 to BMT. The other things are all determined. And as said, the upper bound is based on what? We assume that the active relays cooperate. They don't. but we assume they are. And we know how much are there. So what happens? We have a two-hop communication. To the relays, they're one entity now, and to the end. So that result is actually the optimal approach. So, but it's upper bound. There is, do not cooperate. Achievable rate, again, achievable rate, it depends on the strategy. The simple one is single description. The single description, the more complex one, multiple description. And let's go through them. The simple description. Each so cellular systems could be also annoying, huh? So the simple description. Every distributed relay, hotspot call it, describes its signal via a single way, single code word. And here we have the source transmits two layers. If only one relay is communicated, then the first layer is decoded. If both of them are connected, both layers get decoded. Simple as that. And that's single description. So if we receive, the decoder receive either V1 or V2, it can decode only W1. Receives them both, decodes W1, W2. That can be worked out. For the Gaussian case, looks much nicer. The general formula is for general channels. Here has nothing to do but, again, optimize over power allocations of those radars in general. And again, the idea is superposition coding, this broadcast approach, and this distributed single description CEO problem. What is double description? Again, double description lies in the source, in the distributed source coding, Chen and Berger. Each node has two descriptions. If one node is connected, actually the decoder cannot even decode the two description letter on the rate, only one of them, V, either V11 or V21. And that is enough to decode the first rate. If both are connected, it decodes all four descriptions, and then can decode also the second rate. So that can also be worked out, and in the Gaussian case, surprisingly, because now it's quite an evolved scheme, also can be worked out in details. Everything, including the additional noises due to this distributed source coding with double description. So let's look at some numerical results. Again, we have only two hotspots, two relays, and it's either one is connected or two, as we described. That's the possibilities with the given probability. An upper bound, a trivial upper bound, is using our old results where we take the average over the backhaul capacity, like it was ergodic, which is not. Fine. And we have another worst case Shannon approach, single layer, single description, the worst case of the worst. That we also have. Looking at the results, here is the ergodic upper bound. Here is the other cooperative upper bound. Like both relays were cooperating and they know either one is connected or two, cannot be that. This upper bound you see, while better through the whole region of the probability that we have two relays connected. Probability one relay is just one minus that. But not always better. Sometimes the ergodic for high probabilities beats it. This is the Shannon approach, single layer, single description, independent of the probability that two are connected, your worst case design. This is a single description, broadcast approach, single description. And this is the broadcast approach, multiple, double description. Look how close it is to the upper bound, which is quite nice, obliviousness. And the cooperative thing actually is quite, one wouldn't expect that it be that close, at least I didn't. So this is the point here. Let us try to wrap up or conclude. So whatever we discussed today is cooperation via out-of-band relaying in both ad hoc networks and cellular networks, naive cellular networks, don't forget. And we had quite a few examples here of heterogeneous radios where interfaces, network, MIMO, femtocells, or the other words that come within this general framework, when the focus and emphasis was on robustness, obliviousness, not something that is sealed up to a very special case. And robustness in two meanings. One, imperfect or not at all codebook information, and another, child state information, where here child state was the link, actually the capacities of the links, of the stable links. So we notice that sometimes only minor penalty is paid for this oblivious processing, making it truly an attractive approach. Let's see, just as a wrap-up, what did we use here in basic tools? Wiener Ziff compression, of course, comes into action in the CEO, distributed compression, less sophisticated, more sophisticated, multiple description coding, broadcast approaches, which in general is not that simple a concept, variable to fix, channel coding. Source coding is very simple. And cuts at upper bounds. So, as we said, if we are wishing to step down, actually, to abandon this oblivious, there are many other things that can be done, but this oblivious gives us not only the feeling that it might be maybe a better, a healthier approach in practice, but also sometimes without that, we just cannot generate neither closed form nor sophisticated or nor informative results. Let's put it this way. Maybe the last comment about structuring, where we said, look, and that was at the beginning of the talk, unstructured communication, like you cannot use the fact that the messages comes from a codebook. It's the way structured. That's very nice. Sometimes it's actually dictated, meaning even if I wish to use that, and I know the codebook, know everything, the classical information theoretic setting. For example, what happens on a scalar Gaussian channel? What can we look for more? Scalar Gaussian channel. XI code words that are designed to get the capacity, NI is normalized to get the capacity, classical Shannon formula of that. Optimal code, whatever it is. Random, lattice-based, whatever. Now I ask you, look, one of the interference models is actually you see the very same signal plus another, but it's not SNR, it's something less. Clearly, there is no way that you are going to decode here, otherwise you break the Shannon capacity. But so, who needs to decode? This is an interfering signal. I just want to remove as much as I can its interference. Or, okay, I realize already that I cannot remove it totally because I cannot decode it. How much of the structure can you use here if this is a capacity achieving code? Nothing. How come nothing? That we know via the relation of MMSE and mutual information. Go Shamai Verdu 2005, which means what? The mutual information is an integral of the MMSE, which is the conditional beam function of gamma SNR between 0 and SNR. Immaterial, what is X? And that's on the vector. We have a code board. Gaussian, not Gaussian, doesn't matter. So if we want to achieve here the capacity, because this is the code achieve capacity, this should behave like Gaussian IID. Otherwise, it doesn't work. So, at least from MMC, you try to estimate symbol based on the codebook, based on all the information, useless. You cannot use the structure. So that's something to keep in mind. Thank you.